And in 2023, it kind of makes sense as companies are seeking to use AI in their product services. They want to create ChatGPT-like chatbots to train LLMs on custom data sets. So when ChatGPT was released, probably everybody was curious to know how does the underlying platform look like and how one can leverage it. And this is a video clip from May this year, which kind of makes sense now. So the AI offering in Azure looks something like this. On the top, we have certain problem-solving services. And on the bottom, we have the cognitive services, which are the machine learning models provided as a service. And everything that you see in the red box is actually built on top of a service that is known as Azure Machine Learning Service. So we go through some basics first, because Azure Machine Learning is a mammoth of a service. And so it's basically the machine learning as a service offering in Azure. It uses a mix of user-managed and Microsoft-managed services to function. In AML, you basically create a workspace, which is like a centralized place to manage all your activities and all your machine learning artifacts. You can access a workspace using your browser, or VS Code, or the Azure ML API using the CLI as well. But what do you do on a workspace? You basically work. You can create your Jupyter notebooks, run experiments, you can create and import data sets, create training and inference environments, deploy machine learning models as an endpoint. So you can perform your all MLOps just from the browser itself, so that's pretty cool. And the workspace is actually dependent on certain Azure services on the user's end. So when you create a workspace, there are resources for these services that are created, except for the container registry. So it's not mandatory to have an ACR configured to create or work with the AML workspace. So in AML, data scientists or users would generally run scripts, or they would perform your ML ops, right? And there are various compute targets that are provided in AML for a user to run your Jupyter notebooks, training scripts, or you can host your ML models as endpoints. So clusters are basically managed clusters of VMs with multi-node scaling, and they can be GPU enabled as well. Kubernetes clusters, so you can attach existing Kubernetes clusters, or like the AKS or the on-premises one as well. The attached compute is related to, you can attach your Azure virtual machines and you can run your training scripts and everything on that VM. But specifically for this talk, we focus on compute instances. So compute instances are managed Ubuntu virtual machines that reside in a Microsoft subscription. By managed, we mean that these resources are maintained by Microsoft. So patching of host OS, fixing any security issues if they are found. And the OS image contains various tools, such as Jupyter, VS Code, Docker, Python, and all of these deep learning libraries. So these are used by the data scientists and developers on these compute instances. So basically, this is where you run your code, and you can perform your model training, inference, and all that stuff. So each workspace uses a storage account, which contains machine learning related entities. To access data in a storage account, you can use something that is called a data store. So data stores are basically just references to a workspace's storage account. And you can basically avoid storing your credentials or SAS credentials in your scripts. You can simply use the data store to refer to the type of storage that you want to access. And yeah, that's it. So these are the types of storages that you can access, the file shares and the blob containers. So this is where your notebooks, data sets, any logs, models, they are stored for that Azure Machine Learning workspace. So we can browse the storage account using the Azure Storage Explorer, and you can view the file shares and blob containers. So they have specific naming references. So like you can note the names of the blob containers such as Azure ML-blob store, because this will be used later on. So these are the types of data stores that are mapped to file shares and blob containers. So if you see, the name of the data store is Workspace Artifact Store, and it is mapped to Azure Blob Storage. And this is a simple example where the data store name is Workspace Working Directory. The type of the data store that it is referencing is Azure File Share, and the name of the file share as well. So data stores in Azure Machine Learning support credential-based authentication for file shares. This basically means if you want to work with file shares using data stores, there will be a combination of username and a password that will be used, where the username is the storage account's name, and the password is the storage account's primary access key. Additionally, multiple users can create compute instances in a workspace. And by design, there cannot be two owners for a compute instance. And also by design, any user in the workspace can access other users' files in the same workspace. It's a shared environment, as the file share of the storage account is mounted on all the compute instances. So with this background and a very simple introduction of Azure Machine Learning Service, we begin with the first episode, where a data scientist is looking for their keys. Did you see my keys? While examining the different folders and the files on the compute instance, we come across a directory structure which looks something like this. Now this directory structure is of Azure Batch, and we need to take a quick look into what Azure Batch is. So using Batch, you can basically run your large-scale workloads in Azure with auto-scaling and monitoring. For example, if you want to process images using various computes, then you can use Batch to do it. So nodes are basically virtual machines based on Linux or Windows. When you group up, like a group of nodes is basically called a pool, and you can group nodes together in one single pool. Jobs are basically collections of tasks that are run on a pool, and how the script performs on each run. So for example, if you have a script and you want to figure out what are the metrics when you run the script every time, so you can create a job which runs that script 10 times, and you can figure out how is the performance looking for each and every run. And each and every individual run of a job is called a task. So the task is the computational unit, the unit of the job, and you can monitor and download the output logs for a task. So in Batch, you have a concept of a start task. Basically, the start task runs when the node starts up. The files and the configurations, the outputs of the task are stored in the path in blue. And the error logs and output logs that are generated for the commands that are run in a start task are logged in the standard out and standard error files. As we saw previously, the file share is mounted on the compute instance. So we had a question. How is the Azure file share being mounted on the compute instance? Since data stores reference Azure file shares using credentials, are their credentials being stored or logged somewhere? So the output of the start task is logged in these two files, the standard out and the standard error files under startup directory. So what we found was that the storage account credentials were being logged as is in the standard error logs. And since the commands run as sudo, they would also go in the authorization logs. We reported these two instances to Microsoft and we waited. A few days later, we came across an instance where the password field of the entire command line was masked. Note that the commands that are being executed in the start task are defined by Microsoft. So that was the fix. And that left us wondering, what if there are more such instances of credentials being logged or stored in clear text? Hence, we started looking for more such occurrences. So Azure Machine Learning uses certain agents to manage compute instances. So by managing, we mean diagnosing, monitoring, or making sure that the compute instance is healthy, etc. So these agents are installed on all compute instances, and these are maintained by Microsoft. And they are located in the working directory here. So these agents don't work on their own. These are basically Linux services, and they need certain environment variables or configurations that are supplied in the form of environment variables. And these environment variables are stored in files under working directory DSI. What we found was that the configuration for two of such agents, named DSI mount agent and DSI idle stop agent, they contained the storage account's primary access key in clear text. But why is the environment variable named passwd? It could have been anything else like password or storage account or something else. Turns out that the mount command can source in the password argument as a passwd environment variable. So this issue was found while trying to understand how were the previous issues fixed. Nevertheless, all the instances of storage account credentials being stored or logged in clear text were fixed after our reporting. And that brings us to chapter 2. Since credentials being logged or stored in files was acted upon and fixed, we had a thought. Are there credentials coming in on the compute instance? And we begin chapter 2. Wait, is that my token? So a user can access a compute instance from their browser itself using Jupyter Notebooks, Jupyter Lab, or the browser embedded terminal as well. So all of these requests are basically proxied to the compute instance by a load balancer / proxy in between. So if you want to access Jupyter Lab on a compute instance named AML in the East Asia region, the URL would look something like this. Note that we do not have access to the load balancer's logic here. So this is how the Jupyter Lab terminal, the environment looks like from the browser. And this is how the browser embedded terminal looks from the Azure ML Studio. Oh yes, the default user, Azure user, can easily assume root privileges. So user privilege is not really a boundary here. We'll use this bit later. So these browser-based terminals can be accessed by a user with the proper role-based access control permissions. And the authentication flow for a client accessing Azure Machine Learning Service looks something like this. So the client logs into Azure Active Directory or Entra ID, like whichever works for you. And they are presented, they get the ARM token in the response. So the ARM is the Azure Resource Manager token. And using this ARM token, the client talks to the Azure Machine Learning Services, which in turn generates a new token that is the AML token, which is again scoped just to the workspace itself to perform AML actions. And this token is used on then onwards. So all incoming requests to the compute instance are received by an Nginx proxy that listens on a hard-coded port that is 44224. It has SSL enabled, and it validates the client-side certificates for the authentication as well. And there are certain checks on the subjects and the issuers of the client-side certificate. The proxy checks whether a header named XMS target port separated by hyphens contains a numeric value, and later the value of the header is used to forward the request to the appropriate service. So as you can see, for the incoming requests with the URLs containing Jupyter-related APIs, the request is upgraded to the WebSocket, that's for the terminals, and the requests are forwarded on the basis of the value of XMS target port. Basically, any incoming requests on the compute instance shall have this header populated. This request will be received by Nginx on port 44224, listening across all the interfaces. Based on the value of this port, as you can see, the value in this case is 8888, which is also the default for Jupyter. The request is forwarded to the port that is 8888 on localhost. But the interesting bit here is Nginx logs your access attempts and any errors that are generated in these files in the default path. Cool. So what we found was we were running TCP dump, and we were trying to figure out what happens when we terminate a terminal from the browser itself. And we see that there are certain requests that are sent that get logged in the Nginx access logs. And as you can see in the first GET request, we see that there is a URL parameter named token, which contains a JWT. By decoding the JWT, we figure out that the token is actually related to is of the user itself, of the compute owner, and this was getting logged in the Nginx access logs in clear text, obviously. But trying to figure out why did the URL parameter actually contain the JWT of the user, it turns out for Jupyter Server, you can specify the authentication token in 3 types. So the first is you can use it in the authorization header. The second is you can send it as a URL parameter. And the third is you can specify it in the password field of the login form. We reported this issue of logging of the JWT of the user to Microsoft, and they promptly fixed it. Okay. After all, these are just credentials being logged or stored in files on compute instances. What could go wrong, and what is so risky about it? So developers have been observed to share error or debug logs from their systems on public forums or platforms like GitHub. If they are not quite aware of the fact that these artifacts at times may contain credentials, that too in clear text, that's a silent risk that they're being exposed to. In this example, we see the request for batch error logs, which in our case contain the storage account's credential, the storage account name and the storage account's primary access key. However, this instance is from 2018, so it's a pretty old one. So does anybody recognize this URL? Okay. So this is a URL using which you can access a file which is a tar.gz file, and there's a storage account associated as well, so we'll go through that. This is the storage account name, followed by the accessible services. So under the storage account itself, you can access the blob, file, queue, and table types of storages. The APIs are accessible for the service, container, or the object level APIs as well. And the permissions for this URL, for this SAS token, so there's a SAS token being used in this URL. The permissions is basically you can read, write, list, delete, do all of that on the storage account itself. And the expiry of this SAS token is of 2051. So that URL is actually related to one of the recent news from Microsoft. So researchers from Wiz, they found in June this year an overly permissive SAS token for a storage account on public GitHub repositories of Microsoft. That allowed them to actually use the token to access 38 terabytes of information of the storage account, including backups of 2 former employees as well. So by default, the storage account in Azure Machine Learning is publicly accessible. And based on the container, like the blob container names from their blog, it seems like this is the storage account of an Azure Machine Learning workspace. So based on the container names as Azure ML Blob Store and Azure ML, this is a speculation. So mistakes happen and it's human, but we need to keep learning and try not to repeat them. So dependency confusion attacks with attacker control code has been known there in the news for quite some time now, but they generally exfiltrate credentials that are stored in files. So in this case, we have a nightly build of a popular library called PyTorch, which was compromised December last year. And the malicious binary would basically exfiltrate credentials from files and environment variables. So if you notice, PyTorch is a very popular library that are used in machine learning environments. So if an attacker is able to compromise a file share, they can trivially compromise an entire storage account and the entire workspace too. Let me show you how. So consider a scenario which might be likely to happen. There's a workspace with 3 data scientists, each having 1 compute instance. By design, we know that each workspace user's files are stored in the same Azure file share. If an attacker gets hold of a user, which is a very high degree of compromise, or a compute instance, which had these credentials being stored or logged in clear text, or the Azure file share where your Jupyter notebooks scripts are stored, which are run on compute instances, compute clusters, Kubernetes clusters as well, the entire workspace should be considered to be compromised. Now picture this with a scenario where users could possibly view each other's JWT token. Suddenly the issue feels a little massive. According to the documentation, data stores provide a way to secure your connection information, such as storage account keys and SAS credentials. And using them, you don't need to store your credentials in your scripts. And that's very cool of a feature. However, if the storage account itself, the storage account key itself is being logged in error logs or authorization logs or environment variable files, that kind of creates a difference. And the default user, Azure user, can easily assume pseudo permissions. So user privilege is not really a boundary here. Now the same issue of credential logging may have been in your environment as a silent threat, but on Valentine's Day this year, Microsoft released a CV and they fixed all of these issues. Now, the JWT of the user, of the compute owner, is not even observed to reach the compute instance, forget about the logging part. And the storage account's primary access key is not logged or stored in clear text in any of the files on the compute instance. Some takeaways. Be it logging or storage of credentials in clear text, credentials in clear text is bad. I mean, it's risky as well. As cloud-focused threat actors and like malicious actors, they love going after credentials that are already stored in files. From the design of such environments, we need to be aware of the associated risks as well. So the reviewing of the open source configurations, that is to be done very carefully when you're using them. So supplying the JWT of the user on the compute instance, I mean the JWT reaching the compute instance was still okay, but logging the JWT token in access logs, probably not. Additionally, sensitive sensitive information should not be sent as URL parameters. That's a very well-known thing, and that has been echoed before by researchers as well, as we never know what are the inline components these requests go through if they are getting logged somewhere as well. Additionally, developers need to be aware of possible security implications that may show up while sharing information on public platforms. The issue of credential leakage can turn out to be very critical, especially when users are not even aware of it, as we saw in the case of the recent accidental leak of 38 terabytes of Microsoft AI researchers. With that being said, we now embark on the third and almost final chapter of Spying the Scientist. So in Azure Machine Learning, you can create compute instances in virtual networks. So you can specify the virtual network and the subnet during the creation of your compute instance. This can be an observed scenario where the training environment needs access to or from other Azure resources via private networks and not over the internet. And using VNets is also a very strong recommendation from Microsoft in their documentation. So a simple environment would look something like this. There's a virtual machine, which is a part of a virtual network, And on the same virtual network, we have a compute instance. Let's say the virtual machine on the same VNet gets compromised. What could an attacker from the virtual machine do on the compute instance? Are there any ports open? Let's find out. So we fired up our next favorite tool, Nmap, and we checked for open ports, and we come across a port that is 46802. Remember that we have the compute instances access. So we figure out that the process that is exposing this port is known as DSI mount agent. Okay, the process runs as root. You probably think where this is going if you have been to before the previous Microsoft vulnerabilities in agents, but just hang on. Additionally, this binary is written in Golang. It is closed source. However, we have some debug information because the binary itself is not stripped. So cool. Now we crack open the binary using IDA to understand what is going on. So there's a function called DSI start API service, and we find that there are certain HTTP endpoints that can be accessed. Reminder, there is no authentication required for network adjacent resources to access the URLs that we see on the screen. Okay, so we start taking a look into the different URLs and what do they do. The first one executes the sync command on a file. The second one runs the mount operation. The third one fetches the compute instances image version. But the fourth one lists any systemd services statuses on the compute instance. Examining the services endpoint, one could easily list the status of each service installed on the compute instance. Okay. But we also see that one could see the logs of any service that is installed on the compute instance. At this point of time, a network adjacent attacker could basically list down the services installed, the status of each service, logs for each of the service, and this information could have helped them to perform some reconnaissance, post initial access, lateral movement within such environments. All of that is cool, but just as an example of what all could be exposed, here's a short little demo of what could a network adjacent attacker really see. So while exploring the installed services on the compute instance, we see that Jupyter is installed as a service on the compute instances. Note that this is across all compute instances that you'll be using for Azure Machine Learning Service. And for each service installed, we can view the logs since we are network adjacent and we don't need any authentication for it. There turns out that there were some commands that can be viewed that were executed using the Jupyter terminal. And folks, this is where I went, what did just happen? We saw some commands being logged in the Jupyter service. So basically, an attacker gets on a virtual machine, which is a part of a virtual network. On the same virtual network, we have a compute instance. On the compute instance, we have an agent that is called DSI mount agent. The DSI mount agent can fetch you systemd logs for any service that is installed in the compute instance. So it also exposes an API on a hard-coded port that is 46802. It listens on all the interfaces. So let's say if there is a user that is using any form of Jupyter, be it Jupyter Lab, Jupyter Terminal, Jupyter Notebooks, or the browser embedded terminal as well. And if the user runs any command as sudo, the attacker will send a request to fetch the logs for the service. In this case, it's Jupyter. And in the response, the attacker will get the commands that was executed as sudo by the user on the compute instance using some form of Jupyter. So here's a, okay. So here's, oh my God, just a second. So here's a short little demo of the POC. We call it Hacking the Data Scientist, MLC. So on the top, we have a data scientist running sudo cat shadow on their compute instance. On the bottom, we have a network adjacent attacker who is fetching the logs for Jupyter service in this case, and as we can see, the command was visible from the network adjacent attacker. So if you remember the first command that was being run, it was being run as sudo, the mount command, the sudo mount thing. So it gets also logged in the service logs, and the attacker could view if they were already in the network itself. We reported this vulnerability to Microsoft, and they fixed it. We termed this bug as MLC, as a network adjacent attacker could possibly see the actions performed by a data scientist on their compute instance without needing any authentication being network adjacent, obviously. So this was a funny information disclosure bug. Now, after the fix, the service does not expose the port on all interfaces, and the service can only be reached over the Nginx proxy, which anyway requires client-side SSL certificates. Some takeaways. At times, secret agents may lead to secret bugs, and hence an expanded invisible attack surface, hence a silent threat. So vulnerabilities still exist in cloud agents. So before this, the two vulnerabilities that I remember of are related to cloud agents were in Omigod and WA Linux agent. So there are remote attack vectors as well. So these agents may at times contain certain features that can be the cause of a compromise when we think from an adversarial mindset. Because the logs won't be there, any cloud native logs won't be there how the compromise happened. So deploying training environments in VNets is also a recommendation from Microsoft. However, we found an edge case where there could be like an issue in your environment. So there was a need for focused threat modeling on the features that we provide to such agents that are installed in these sensitive environments as well. Practicing zero trust is hard, but it's very crucial for cloud security. So the essence of zero trust is that do not assume that just because something is there in your environment, it should have access to other resources in your environment. And so, yeah, sometimes simulating attacks, even in secure configurations following the documentation, may uncover vulnerabilities in the service itself. Okay, so now we are on the last chapter, that is, can you really see me? And I had to put this because why not? So let's say we have a virtual machine and a compute instance, and we want these Azure resources to access certain other services. One of the ways is to hard code credentials, but that's not a recommended way. Microsoft, in fact, recommends using something that is called a managed identity. So the logic behind managed identities is that if you want your application to access a resource, the application will talk to a managed identity service and it will fetch a token. And then it will use the token to talk to the resource that the application originally intended to talk to. And you as a developer don't need to hard code your credentials in your applications or scripts. So this is pretty cool. It's similar to the instance metadata service. So managed identities are of two types. A user-assigned managed identity is basically, it can be assigned to multiple resources in Azure, so it can span across resources. And a system-assigned managed identities are only tied to the resource itself, and only that Azure resource can request for tokens. On a compute instance, one can sign in using managed identity using the Azure CLI. And using managed identities, you can assign certain privileges to the identity on the resource to be able to do things like accessing other Azure resources. So this is how you can log in using the identity, and I was curious to know what happens behind the scenes. How does the traffic look like? So we ran TCP dump and we were checking for any outbound traffic when we run az login -- identity. And we get this GET request and some interesting headers. There is a header that is containing some sort of secret, and it is sending the request to a local port itself, that is 46808. But since we are already on the compute instance, we figure out that there is a process named identity responder D, probably daemon, which is listening on this port. From this binary, we are able to figure out the service that is underlying, and we see that there are certain environment variable files that are being used as well. The name of the service is Azure Batch AI Identity Responder Daemon. Okay, it also logs the output and any errors that are generated to syslog. So that's helpful. But we are talking about responding identities. While understanding the binary, we found that the binary fetches the secret and the endpoint from this particular file at etc environment.sso. But how does the final request look like? Because even now it is still going to the local interface, right? For analyzing the binary, just for fun, I had a moment of deciding whether to dump the process, check the logs of the service, or reverse the binary. But since this is our game, we set the rules here, so let's just go all in. So this is from the logs, and we see that there is a file being read at azmount.nbvm, and there is a token that is being fetched from this public-looking endpoint. So these are the two files from where the environment variables are also being fetched for this binary, and we figure out that this is the post request that is fetched, that is used to fetch the AML JWT. Okay, so we have the compute instance name as instance ID, and the resource for which we are fetching the Azure AD token. And there are certain certificates and private keys that are used from this hard-coded path, like the startup certs. So, in a gist, the identity responder talks to an endpoint that is defined in the cert URL and environment variable using a pair of certificate and a private key. And it gets the AML JWT in the 200 OK response. So this is how it works. Let's say the certificates, like the certificate and the private key are stolen post-compromise on a compute instance. So there was a thought whether these certificates can be used from non-Azure environments or not. And turns out it was not possible, so we got a 401 unauthorized. So the assumption was that the certificate and the private key is tied to the compute instance. And we did see that each created compute instance had a unique certificate thumbprint already. So that's cool. But does the story end here? Not yet. We're just getting started. So have you played this game called Return to Castle Wolfenstein? Probably not. But we'll play a game called Return to Castle DSI Mount Agent. So we now take a look into our good old friend, and the service fetches its environment variables from a file. So this is the same file where we saw the storage account credentials being logged in the first episode. This agent runs as a service on every compute instance, and the environment variables look quite interesting. We have something cool going on here. There are certain keys, certain certificates. There's some XDS endpoint. What is happening? Checking the systemd logs, we see that the DSI mount agent basically checks and mounts the Azure file share of the AML workspace on the compute instance, and it runs as a daemon and checks every 2 minutes whether the file share is mounted or not. Cool. Turns out that the DSI mount agent talks to a public endpoint that is defined in this environment variable in the file using the pair of certificate and private key that we saw from identity responder daemon. And this is how the post request looks like while examining the outbound network traffic from the compute instance. And we see that there is a specific part here in the post request body where the request type is set to get workspace. So we'll be ignoring the top URLs and the headers because they are same across all that we'll see ahead. So by reversing the binary, the DSI mount agent binary, we figure out that the function name is get workspace info, and the response contains certain metadata about the workspace. So this can be considered like the who am I of the AML workspace. So we have certain resource IDs, workspace IDs, tenant IDs, subscription ID as well, and some private link information. Later, when we were just debugging the agent, and then we saw this one request that is called get workspace secrets. What secrets are we talking about? And this looks a little promising. In the response, we get the storage account name and an encrypted JWT, which is also called a JSON web encryption, like the JWE format. And since we had the storage account name, it seems like this is the encrypted form of the storage account's primary access key. But let's find out. Upon understanding how the decryption of this token happens, so there is an encrypted symmetric key and a private key that are defined in the environment variable files. So first, the decrypted symmetric key is fetched, and using the decrypted symmetric key, the response that we saw in the previous slide is decrypted to fetch the storage account's access key. And for this, I thank you, David. So David is my colleague, and he helped me with the reversing of this aspect. So the certificate and the key and the environment variables can be used to fetch the storage account's access key. And if these jewels are stolen from your environment, somebody from non-Azure environments could do the same. So what happens when you rotate the storage account's primary access key? So this is one of the ways how you can harden your environments when your storage account's key is leaked and you just rotate the environment, like rotate the key itself, and you can use the rotated key elsewhere. So here's a short little demo. So we are on the Azure Machine Learning Workspace portal, and we see that there's an associated storage account. So for the storage account, we'll be going to the access keys section, and we'll copy the primary access key that is already there for this storage account right now. So we copy it to my terminal that is on my laptop. I have the certificates and the environment variables exfiltrated on my laptop from a compute instance, and I run my POC to fetch the decrypted storage account key basically that we saw. Now, I will basically rotate the key. Yes. So I will regenerate the key, and it's rotated. And after rotation of the key, I need to synchronize my Azure Machine Learning Workspace to work with this newly rotated key. So I'll do that from Azure, from this shell. So after the synchronization has happened, I will rerun my POC to see whether I can use the same pair of certificates to fetch the credential again. And we see that that is possible. So even rotating the keys won't help. So if your jewels are stolen, and even if your jewels are stolen, even rotating your storage account access keys won't help, and this is already quite persistent. So is there a way to track the usage of such certificates and environment variable combinations from non-Azure environments? We'll get to that in a bit. But let's find out what else can we do. So the function that we saw named getWorkspaceSecrets calls another function that is called generateXDS API request schema. So this function is basically used to generate the post requests body itself. So the idea was to list all the cross references to the function which generates the post requests body. So we had some candidates here, like get ACR token, get ACR details, some other get application insights key and all that stuff. We stumbled across one such function in one of the agents called get AAD token. So this looks promising since we can possibly fetch the Azure AD token for some sort of Azure object. And to figure out how does the request body looks like, we debugged the agent to find the arguments being supplied. So our request looks something like this. We have the request type set to get AD token, and the request body parameter contains another JSON which has the resource for which we want the Azure AD token, which actually makes sense. And in the response, we got the system assigned managed identity token if it is assigned to the compute instance. So this was a little out of scope for the talk, but it's a recent development. We could specify the client ID in the request body parameter itself, and we can also fetch the user assigned managed identity token as well from non-Azure environments. As we saw earlier, user assigned managed identity can span across resources, and at times they may be overprivileged. So the compromise of the certificate plus the key and plus the files containing environment variables can lead to fetching of the Azure AD token of any type of identity that is assigned to the compute instance. But why does all of it matter? While skimming through the documentation, we come across this particular statement that when you assign a managed identity to an Azure resource, only that Azure resource is supposed to be able to fetch the token for that identity just from that resource. But in our case, we were able to do it outside the Azure environment, like outside the Azure resource itself. So a quick recap, because there was a lot of things here and there. So the DSI mount agent talks to a public endpoint using a pair of certificate and a private key. And the DSI mount agent can perform the who am I of the ML workspace. It can fetch the storage account's primary access key and the Azure AD token, Entra ID token for any assigned managed identity and much more. And so could an attacker if they had access to the certificate and private key from non-Azure environments as well. So this is a demo of how you could do it. So on the left, you have two folders called SAMI and UAMI. So these are the system assigned managed identity and the user assigned managed identities. So these are the certificates that I have exfiltrated from two compute instances. And as you can see, I'm able to fetch the storage account key from one of the folders. So this is happening outside the compute instance altogether. And now I can fetch the who am I of the AML workspace, like where else this workspace is being used and what are the different resource IDs for all the other Azure resources. And now we will fetch the Azure AD token of the system assigned managed identity. So I'll run AML dumper 2 in this case. So we get the JWT of the managed identity outside the Azure boundary itself. So how do the logs look? Let's say we are fetching the JWT of the managed identity using a legitimate way from the compute instance itself. So this is how the code will look like. And this is the malicious activity where we are fetching the token from a non-Azure environment. So maybe the logs will help? No. The difference, these are the diffs of the logs that are generated between the two activities. And we see that there is no sign-in, there is no IP address in the sign-in activities as well. So the identities could be, so the logs were basically almost identical. The location info was missing. The certificate that we saw is actually valid for 2 full years. And to invalidate the stolen certificate, you need to delete the compute instance. And if there are any over-permissive identities being used, it can open up avenues of lateral movement, privilege escalation, and all that jazz. So some takeaways. You need to have your cloud service logging enabled and in place. The logging for managed identity usage can be done better. The scoping of identities should be following the principle of least privilege. And defense in depth with respect to cloud environments is a very good win. We'll see why. And threat modeling environments for possible scenarios of compromise can help you at times uncover such design issues as well. We found some bugs that do not or rarely make the news, and they get silently fixed as well. We tried few angles as well, but where do we go now from here? You need to set up your environment using the best practices, using VNets, private links, private endpoints. Now if you think the storage account access key getting logged, the JWT getting logged, the agent exposing sensitive information in VNet environments, all of these could have been curbed if your environment is properly configured. And having your defenses in place obviously can help you reduce and eliminate such issues at times. Following secure deployment strategies definitely ensures defense in depth, and it is quite effective against the possible silent threats that we just saw. In fact, Microsoft made it easy to go secure by default by offering these network isolation options while creating an AML workspace in the Azure portal itself. Additionally, you need to monitor your cloud environments for changes, any storage account keys getting rotated, any public or anonymous accesses getting enabled using CSPM tools as well. You need to you need to set up logging using cloud native solutions. You can leverage existing frameworks like Azure Threat Research Matrix as well, Storage Matrix as well, we'll see in a bit. Trust but verify. So the paradigm for security when it comes to machine learning and environments these days will fall down to the integrity of the artifacts that we are using in the environment. So the integrity of Jupyter notebooks, if they are modified, scripts, data sets, and all that stuff. And there's a very different attack surface when it comes to these environments as companies will go to use these. And obviously, you need to examine managed services to uncover such issues and obviously implement the principle of least privileges, like use custom roles, don't go by the default roles, the default policies and all that stuff, because at times they are overprivileged and you may not be even aware how you got compromised. So specifically for machine learning environments, you can leverage the Atlas framework, which is the adversarial threat landscape for artificial intelligence systems. Think of these like the MITRE ATT&CK framework, but for machine learning environments. As companies will tend to move towards leveraging such cloud services, it's important that we don't mess this up. So the threat matrix for storage services actually contains known tactics, like known TTPs that adversaries may use against these types of accounts. So these are certain resources to begin with. Atlas, in fact, also enlists various case studies and around simulation and incidents that are focused on machine learning environments, which can help you in understanding what are the threats that will be there for your deployments as well. So these are two of my favorite case studies. Falling down to acknowledgements, family members, friends, and my colleagues for helping me out in times of doubt. Zero-day initiative for triaging and smooth communication of the bugs with Microsoft. And there are a few more bugs in the disclosure pipeline that we are excited about, so stay tuned. It's not a question of if a vulnerability or an issue like this gets exploited. It's a question of when, and we need to really secure our present first. With that, thank you so much for attending my talk.